Hello everybody, welcome back to data analysis. So today we're going to talk about prediction and confidence intervals. That's going to be the first part of this lecture. The second part we're going to talk about alternative measures of model fit. This is sort of to contrast RMSE, which we spent a lot of time talking about. Some references in the course text. Okay, so as a quick introduction, let's recall the places we've been. So we've seen that if we have the normality assumption, this mean zero, constant variance, independence of epsilon across observations, and then epsilon being normal, we've seen that both of these pieces are Gaussian, right? That is, the least squares estimator itself is Gaussian, has some certain mean, right? The fact that the mean of the least squares estimator is what we intend to estimate means it's unbiased, and then we have a certain covariance matrix here. And we also have that the predictions, y hat, are Gaussian. This follows because y hat is a linear combination for any fixed x. It's a linear combination of a Gaussian random variable, beta hat, and some fixed, so it's a fixed, so x is some fixed linear transformation, beta hat is Gaussian. We have y hat is a linear combination of Gaussians, and hence Gaussian. So we also have, and this is what we saw in the last lecture talking about hypothesis testing, we saw that if we, so in general it's a problem that we don't know this constant variance piece. But we saw that if we plug in an unbiased estimate of sigma squared, that is this one where we correct for this number of parameters we're estimating in our MSC calculation. This is y minus y hat squared, right? So this is our estimate of the variance. This is our unbiased estimate. Then we get t distributions above, and when I say we get t distributions above, I mean right. It's not this. You plug in this unbiased estimate of the variance. You get a t distribution because the t distribution is an analog to normal 0, 1. And so what I mean by that is when we plug in the t distribution, we get that beta hat I minus beta I over the square root of sigma squared. I'm plugging in my variance term here. Square root of, here I'm plugging in our estimate for the variance, x transpose x inverse, and then here this becomes a I plus 1. The reason being that we have a 0 in the beta indices, whereas our diagonal terms along of the variance start at 1. So what I mean is, when I say that we can plug in the unbiased estimate, we get t distribution, I mean that this thing is distributed t n minus p minus 1. Okay, and so we saw this in the last lecture. Similarly, we can do the same thing for this y hat, the prediction, and we get, right, so we route y hat minus its mean divided by its standard deviation. We get to plug in our estimate of the variance, selecting the appropriate term along the diagonal. Then we also get a t distribution here. Okay, so in this lecture we're going to use this property to form confidence intervals, right? So we have a distribution of beta hat I, and we can use it to form a confidence interval for beta I. And in particular, the confidence interval looks like this. Okay, so I'm just going to break down these pieces. The first one. So actually, let me just introduce this equation in the context of what we've seen before. So this is from your intro stats class. You've seen the confidence interval for the mean and what that looks like. And typically we write it as x bar minus z alpha over 2 times sigma over square root of n, x bar plus z alpha over 2 sigma square root of n. Right? So this is our the confidence, probably the first form of the confidence interval we've seen in our intro stats class. And so what this is, if you remember, is we have some mean mu is in this interval with probability 1 minus alpha. And so the argument is that if you look at, so the z alpha over 2 piece is something that, so if you have a standard normal distribution, it is the z alpha over 2 is the 1 minus alpha over 2 quantile. So z alpha over 2 is the piece where, is the z value where you have alpha over 2 probability in the right tail. Okay? And then the sigma over square root of n here is actually the standard deviation of the mean. So what happens is the standard deviation of x is sigma according to the central limit theorem, or you can just look at it as properties of variances. You divide by square root of n to get the variance of the sample mean. Okay, and so what we have is actually very similar to this. So what we have is beta instead of mu belongs to this interval. So here we have estimate minus a t quantile instead of a z quantile, and then we have actually this is a sample standard deviation. The reason that this is a sample standard deviation is because this is, if I can flip back a slide, this is exactly this expression, the variance term, plugging in the estimate of the variance that we have, and then taking a square root. So taking the square root of the variance gives us this. Okay. And then so we subtract and we add. So this is our confidence interval. And you can actually convince yourself why this is appropriate, because if you rearrange this, what you can show is that this is equivalent to beta hat I minus beta I, this is just with a little bit of algebra, over square root of our estimate of the variance so this is transpose x inverse, I plus 1, I plus 1. Okay, so what you can, if you rearrange this with some algebra, you can show that beta I is in this interval if and only if this statistic here is between t alpha over 2 and so it's less than that t alpha over 2 and greater than negative t alpha over 2. Okay, and here I've just omitted, it's a little bit bad form, but I've omitted writing the degrees of freedom. They just carry along over here. And this piece in the middle here is has a t distribution from the previous slide. So if this has a t distribution, this is saying that this thing with the t distribution is less than the 1 minus alpha over 2 quantile, greater than the alpha over 2 quantile with probability 1 minus alpha. And if you just draw the picture of what the t distribution would look like, that you can convince yourself of that being true, because what we're doing is we're basically saying this thing, which is distributed t, is we are saying it's greater than this negative t alpha over 2 piece, less than this t alpha over 2 piece with probability 1 minus alpha t. And since we're throwing away alpha over 2 in each tail, we're just left with alpha. So there's alpha over 2 in this tail, alpha over 2 in this tail, probability alpha in the middle. Okay. So this is the expression for confidence interval for a beta term, right? So if we want to find a confidence interval for a certain coefficient, right, we can use our estimate assuming that we have the Gaussian error assumption, right? So again, we have to check our diagnostics, but we can form a confidence interval that looks like this for this coefficient. Okay. Similarly, we can also show that the mean of y given x, okay, that is the mean of y given x, it is x beta, the ith piece, okay. It belongs to the following interval, okay. So that is mean minus t distribution, standard deviation, mean plus t distribution. When I say t distribution here, I mean a t quantile specifically, times the sample standard deviation, right? And again, this piece follows exactly as above, using the second piece on the last slide. So on the last slide, right, we have y hat. Our prediction is mean x beta, covariance matrix given by this matrix here, right? If I plug in this estimate of the variance term, this becomes a t distribution, right? Sort of, and here I'm saying again, y hat minus x beta over the appropriate term along the diagonal here, where we've plugged in our estimate, is t distributed. Okay. So that's what we have going on here. We have the mean of y given x. This is the ith term in the prediction, okay, x beta. And here we plug in our estimate. Okay. Here we have the t quantile sample standard deviation estimate, t quantile sample standard deviation. Okay. So again, if you do that rearrangement like I just talked about for this top piece, you can show that you quickly can find something that's distributed t is bounded between two t quantiles, and that occurs with probability 1 minus alpha. Okay. So this top interval is a confidence interval for beta I, the coefficient, and this bottom one is a confidence interval for the mean of y for some fixed x. Okay. So if you give me an x, okay, I will compute my estimate, and then the estimate actually, so that estimate matters because this hat matrix here, which we've seen before, this hat matrix depends on the x quantity, the design matrix, and so yeah, this is a 1 minus alpha confidence interval for the mean of the prediction given x. Okay. Okay. So we can obtain confidence intervals, okay, for both beta I and x beta I. Okay. Beta I, that's this x beta I is the same as the expected value of yi given x. Okay, the ith prediction given x. And so another important interval that we'll want to construct is called a prediction interval. And a prediction interval will contain y. Instead of containing the expectation of yi with a given probability, I want to contain yi, the actual observation, with a given probability. This is called a prediction interval. Okay, it's different from the confidence interval because a confidence interval you want to contain a fixed constant value with a certain probability, that is an expectation or a constant slope beta. And for a prediction interval, it's an interval for a random quantity. So yi is random, but we want to find an interval which contains it with a certain probability. Okay, so we can find a distribution for the prediction interval by showing the following. So if we show that y minus x beta hat is distributed normally with variance sigma squared I plus the hat matrix, okay, then a 1 minus alpha prediction interval will be exactly as follows. We'll do y minus, so this is y minus its estimate, so its estimate term here, t quantile, appropriate sample standard deviation, and then estimate t quantile, appropriate appropriate sample standard deviation. Okay, so here the procedure is almost exactly as what we've done before. We just have to show that this y minus x beta hat is distributed normally with this variance covariance matrix. Okay, so let's do that. I'm going to let epsilon subscript old, okay, denote the noise in the sample used to estimate beta hat. Okay, so just to break down what I'm showing here, so there's sort of two sources of randomness here, right, in this y and x beta hat. X beta hat depends on some sample, right? We have some samples of x's and y's. There was some epsilon in there that govern the relationship between my x's and y's. And so what we have here is two sources of randomness. There's what I'm going to call epsilon old. Epsilon old is the randomness that was used to generate beta hat, and then I'm going to call epsilon this new randomness. This is the randomness in this observation y. Okay. So y is this quantity distributed normally, and again, I should say this is under this third assumption. Okay, we are using the third assumption a lot of places here, and so I just want to make it explicit. This third assumption, of course, is the Gaussian error assumption. So let's start with y minus x beta hat, right? Well, we can write it as y minus, so this is the prediction of y, right? This is this x beta hat is the predictions y hat, okay? And y hat in general is hy, right? This is the relationship between the hat matrix, which we've seen in previous lectures, that y hat equals hy. The hat matrix puts the hat on y, right? So the relationship between the predictions for our original randomness epsilon old is y hat old equals hy old, okay? So this is our original y observation used to build beta hat, and then we have a new y observation, this y here, okay? So what I'm doing is I've taken y hat is hy, and then y can be expanded as, well, x beta plus epsilon according to the relationship that it satisfies with x beta. Okay. Opening up here, we can expand y, this y old, this original y's, into x beta plus epsilon old. This depends on some original randomness, some new randomness, some new epsilon, right? And then I can collect terms. Okay. So expanding out the hat matrix, which is x transpose x inverse x transpose. Okay. I get two pieces which cancel. So this x beta just becomes x beta. Okay. So we have x beta plus epsilon minus x beta minus the hat matrix times the original randomness, and more cancellation, we get epsilon minus the original epsilon. Okay. So what we've shown is y minus x beta hat is distributed according to, right, epsilon minus h epsilon, and this is our original and our new. So this quantity, of course, is mean zero. If I applied an expectation to it, both of these epsilons would have mean zero. Okay. And then the variance of this piece I can actually show is the following. It's sigma squared I plus the hat matrix times the transpose of the hat matrix, and then because the hat matrix is symmetric and idempotent, we've shown this in a previous lecture, this becomes h squared, which is equal to h. Okay, so the reason that I can do this is the variance of epsilon minus h epsilon old right? Well, these are two different realizations of epsilon, right? And according to the third assumption, the epsilons are independent across observations. And so if they're independent across observations, we can split up the variances according to our properties of variances for independent random variables, h epsilon old, right? And of course, this negative is constant. We can pull it out. The variance, right? I can just remove this negative. The variance of this epsilon term here is sigma squared times the identity. That's here. Okay. The variance of this piece, what I do is I pull out an h and I put an h behind, and then times the variance of epsilon old. So this is just some properties of variance we've seen before. I get an h, sigma squared identity, h transpose, rearranging, that's this piece here. Okay. So the thing about the hat matrices that I was describing is that, right, if you remember that the hat matrix is symmetric, meaning h transpose equals h, and the hat matrix is idempotent, meaning h squared equals h, well, what we can write this piece as is h transpose, because h transpose equals h, I have h squared, and then oops, I've written this incorrectly. Not h squared equals the identity, but h squared equals h. This is the idempotency. So I can rewrite this as h squared according to symmetry, and then h squared is equal to h by idempotency. Okay, so that's rewriting here. Okay. Lastly, so I have this quantity is mean zero, has a certain variance. Lastly, it is a linear transformation of Gaussians. This is Gaussian, this is Gaussian, linear transformation of Gaussians. Hence, it is Gaussian. So this random variable is mean zero, variance covariance matrix given here, and Gaussian. So that is what I want to show. That is mean zero, variance given by sigma squared I plus h. H is the hat matrix, and then this random variable is actually Gaussian. Oops. Okay. So let's actually return to the body fat data. So the body fat data set we've seen in a previous homework. It is measurements of like bicep circumference and waist circumference and all of these different things for I think 200 men in a certain study. Okay, the idea was that we wanted to predict percent body fat, which is generally expensive to measure, using easier to measure attributes like waist circumference and things like this. And so let's say we want to use our model to create new fitness guidelines, and so we want to quantify the error in our estimates, right? And so if in this example, if we want to come up with a model which was we're predicting y percent body fat from some betas plus some measurements. Let's say we say that waist is important, and we say that this is unsurprising, maybe the height is important. So if we said, well, we want to predict percent body fat, which is expensive to measure, you have to stick somebody in a tank filled with water to figure out their body density, which will give you their percent body fat. Well, instead, we're going to estimate this using these observations with a linear function of waist circumference and the individual's height. And I have written this a little bit incorrectly here. I just needed x. Okay, so just estimating these betas is important, but also coming up with confidence intervals for our estimates and for our predictions is also important. And so what we'll do here, here's the interpretation, right? So in general, we want to know for these coefficients, right, how much do changes in our predictors change our predictions? Okay, that's their interpretation, and we can use confidence intervals for these coefficients to bound the errors here. And the interpretation of the prediction, right? This mean term, this we estimate as a conditional mean. What is the expected body fat for an individual with certain attributes? So if you tell me somebody's attributes, somebody's height and weight, then I'm going to form a confidence interval for the mean of y. That is, I'm going to find a confidence interval for the expected body fat for an individual with these attributes. Okay. And then this prediction interval is actually, we want to find what is the actual body fat for an individual with certain attributes. So this is important, okay, because let's say that I was going to actually use, this example to set up new standards. I can't use the confidence interval here to find a window to cut people off, right? I would say, okay, let's say you've got to be, in a 95% confidence interval of this attribute, of this number, to be considered within standards, let's say. That's something we might do. If we used a confidence interval here, we'd be making a mistake, because we wouldn't be collecting 95% of individuals, right? We would be 95% confident that this confidence interval would be we would not be 95% sure that the confidence interval contained this fixed value, the mean, instead of containing 95% of new individuals. Okay, so the prediction interval is finding a window containing this random quantity y, whereas the confidence interval is an interval for the mean. So this is subtle, okay, so please just note it. Prediction intervals are for the random quantity y. If we want to find an interval which contains 95% of individuals, that would be this one. If we want to find the predicted value with 95% confidence, we would use the confidence interval for the mean here. Okay, so how do we do this in R? In R, we use confint to get confidence intervals for the coefficients, okay, and we use predict to get confidence intervals for the means and prediction intervals. Okay, so we can add an extra argument to the predict function to get confidence intervals, and I'll show you that in just a moment in an R example. And so this body fat example that I was just working on, we're going to actually do this problem. Quick reminder, we need the Gaussian error assumption for any of these results to be valid. Okay, so let's jump into R. So I'm going to load up the body fat data into this data frame DF. Quick reminder, what we're working with here, we have density, which is an expensive measurement to acquire percent body fat, generally expensive to acquire, and then everything else is pretty cheap to acquire. So we can, grab a tape measure, throw it around somebody's neck, measure their neck circumference, throw them on a scale, get their weight, so on and so forth. So if we want to define, so the idea is that we want to predict percent body fat using some of these cheaper to acquire attributes. So how would we find confidence intervals for the coefficients? Okay, I'm going to build a linear model here called LM1, predicting percent body fat from hip circumference. And then if I run confint, feed in LM1, and say level equals 0.95, level equals 0.95 says I want a 95% confidence interval. Here I get confidence intervals for my betas. So I have this is the lower bound, and this is the upper bound on the confidence interval. Lower bound for the confidence interval, upper bound for the confidence interval. So this is beta 0, the intercept, and beta 1 for hip, the hip coefficient. Okay. If you omit level, confident will give you a 95% confidence interval by default, but it will also tell you here. So this is the 97.5% or 97.975 quantile and the 0.025 quantile, and it tells you, so you can quickly see, okay, alpha over 2, I have 95% confidence interval here. For confidence and prediction intervals, I mentioned we use the predict function. So what we do is we do predict, okay, and then LM, so I'm going to feed it my linear model, and then I'm going to say interval equals confidence. So this gives me confidence intervals for the mean. Okay, so lots of predictions here. So what I have is the fitted, lower, and upper bound. Okay, so this is my beta hat. This is the beta hat. This is my y hat. This is my lower bound determining the confidence interval, and my upper bound determining the confidence interval. Okay. To form a prediction interval, we have the exact same, but with interval equals prediction instead of interval equals confidence. So let me just wrap this in head so I can make this smaller. So quick question to test your understanding. Which of these is going to be bigger, the confidence interval or the prediction interval? Okay. Well, if we jump back to the slides real quick, let's check. So the prediction interval is formed by, has variance sigma squared I plus h. We plug in the corresponding estimate for the variance as we've been describing to get a confidence interval. A confidence interval. I should be very clear. Prediction interval. I misspoke. This is a prediction interval, not a confidence interval. Okay, so this is the prediction interval. To find a confidence interval for the mean here, we have y hat is normal, mean as before, variance sigma squared times the hat matrix. So we see that between the confidence interval for the mean and the prediction interval, we go from variance sigma squared h to variance sigma squared I plus h. So we're increasing the variance in the prediction interval by adding this identity term. Okay, so that tells us that we're going to have higher variance in the prediction interval, which means we're going to have a larger interval. And so let's just verify that. So if I run the confidence interval and then I run the prediction interval, well, I see obviously the fit should be exactly the same, right? The lower bound for the confidence interval is much higher than the lower bound for the prediction interval. The upper bound for the confidence interval is much lower than the upper bound for the prediction interval. So here we see that the prediction interval is much larger than the confidence interval in general. Okay, so that is, and so just a quick reminder what this is. This is an interval which will contain the percent body fat of individuals with the x attribute corresponding to the first observation. That is a given individual's hip circumference, okay, with a certain probability. Here this is 0.95, right? We can specify with an additional argument, which is level here. Okay, and perfect. So let's plot these confidence intervals and prediction intervals. So to do this, I'm going to build a quick sequence of the x values, which in this case are hip circumferences, sequence going from min to max hip circumference, and I'm going to predict on this this hip range going from the min to the max of hip values in the data frame. Okay. Save the prediction intervals, and let's make this plot. So here I'm plotting hip circumference against percent body fat. Here's the fit in black. Here's the lower bound associated with the confidence interval in blue. Okay. Here's the upper bound associated with the confidence interval in blue. Okay. And just what I'm doing here, just so if you can follow along with R, what I'm doing is I'm plotting the fit column in the confidence interval. Remember, we saw in this confidence interval, this outputs some data frame which has fit, lower, upper. So I'm just extracting that information, plotting fit, lower as a blue line, upper as a blue dashed line. Okay, and then doing the same thing for the prediction intervals in red. Okay, So again, this interpretation is important. I'll zoom in really quickly. I think this is a nice graphic. Actually, let me add the legend before I do. And my legend is a little wonky, so that'll make it a little easier to read. And then, so what's happening here again is this prediction interval contains the points with 95% confidence. So what's happening is, if you fix me an x value, this confidence interval determined by the top and the bottom here, prediction interval formed by the top, the red line and the red line. This prediction interval contains the black points with 95% confidence. And then similarly, what's happening with the confidence interval, it's a little different because we're estimating, instead of wanting to contain the points with 95% confidence, we want to contain the true line that goes through these points with 95% confidence. Okay, so instead of fitting the points, we are fitting this true line that goes through them, which is the conditional mean. Okay, and we see that the blue line is much narrower. The goal is we want to estimate this line, which is a constant, doesn't depend on epsilon, it's just some true value we want to know, as opposed to an interval containing some random quantity, which is the prediction interval. Okay? All right. And so let's just do really quickly to make sure we're going to sanity check what R is doing. I'm going to actually compute the confidence intervals using the quantiles that we've discussed. So my alpha is 0.05. This gives me a confidence interval of 0.95. Okay, I'm going to get my estimate of the standard deviation, this S. I can extract that from the summary of the linear model in R. I'm going to get my design matrix from this linear model, X. Okay, my T alpha over 2, my T quantile, so I'm going to plug this into QT. This will give me a T quantile. My P is alpha over 2. My degrees of freedom is n minus p minus 1. Here p, because I only have a single predictor, p is 1, so this becomes n minus 2. And then I'm going to take a right tail there. So my right tail is alpha over 2. Okay. And then to actually build my confidence interval, I'm going to say my estimate, beta hat, minus T alpha over 2 times this sample standard deviation times the square root of the appropriate term along the diagonal of x transpose x, inverse. Okay, so this is x transpose x, and then the solve will take the inverse of it, taking the appropriate term along the diagonal. Okay, and the same piece added instead of subtracted will give me my upper bound. Okay, so here's my estimate. So this is my lower bound for the intercept term, upper bound for the intercept term computed manually. Just comparing it to what R does, we see, unsurprisingly, these numbers match exactly. So we've just replicated what R is doing under the hood and verified that indeed it's the calculation that we have from the slides. Okay, a confidence interval for Y. So that is Y given X. That's forming these blue lines in this picture here on the right. Here I'm going to build the hat matrix. So X transpose X inverse, X transpose. I'm going to take my prediction, X beta hat, and then I'm going to subtract off the appropriate T quantile times the estimated standard deviation times the appropriate term along the diagonal of the hat matrix, and add for the other side. This matches what we have in the slides. And so, and then I'll just wrap this in head so we can see we don't have such an unmanageable output. So here we see the first 6 doing the same they're the same with R's automated confidence interval for the mean Y given X. We have again exactly the same numbers. Let's see, this first row matches exactly, and so on and so forth. So we have the lower bound and the upper bound. So again, we validated what R is doing under the hood. In general, you don't have to bust out all this machinery and do this manually. I encourage you to use R's tools by default, but indeed we've validated the expressions that we had on the slides. Same thing for the prediction interval. It's very similar, except for instead of just having square root of the diagonal of the hat matrix according to the expressions on the slide. Remember, we had the identity matrix plus the hat matrix. That forms our variance covariance matrix. So here I'm adding an identity term plus hat matrix, and so I see, and again I'll add some shortcuts here to make this a little bit easier. And we see that we are matching exactly. Okay. So we have double-checked R. R is doing what we'd expect, and we can replicate its results manually. Let me talk for just a moment about a warning that you may have seen as I'm making prediction intervals. So what this prediction intervals is saying, okay, well here, predictions on current data refer to future responses. Okay, so what R is warning us here is actually, notice that when we derive the prediction interval, we had these two sources of randomness, epsilon old and epsilon, right? This epsilon used to build the least squares estimator beta hat. Okay, I got some certain x and y pairs, and then the idea is I wanted to form a prediction interval for new y's. Okay, so there's randomness here, and then randomness in this new y that we're receiving. So what R is warning us is R is saying, hey, you just formed a prediction interval on the data used to build the model. So you formed a prediction interval on the data used to build the model, okay, and it's just warning us that, hey, these y's, the prediction interval, it assumes that your y's are new, and so if you are using the same data to build the model and then look at your prediction intervals, you're basically reusing this epsilon old twice here, which is not how the derivation goes, right? And so this is just a quick warning that it's referring to future responses, y responses, not these current y responses we have on hand. Okay. Okay, so let's see. That is what I have for now. Let me just double check here to make sure that. Oh no, I have one more example that I want to revisit. So jumping back into the slides, here's a neat example. This is a Dinosaur application, and so the question is this. This is actually quite interesting, and I found this sort of randomly as I was looking at my random interests. So the question is, were dinosaurs warm-blooded or cold-blooded? And if you are a paleontologist, actually this is a pretty contentious question. There are two different camps. One camp of paleontologists believes that dinosaurs must have been warm-blooded, endothermic, that is, their body generated a certain amount of heat internally, and then another camp believes that dinosaurs were cold-blooded, similar to like lizards, how lizards have to stay out in the sun and get warmed up so that they can function. There's sort of arguments for each direction. In particular, biologists have noticed that endotherms, warm-blooded animals, in general, they have to have higher rates of blood flow to maintain the high metabolic rates that are required for being warm-blooded. So these endotherms have high rates of blood flow, and as a result, warm-blooded animals have vascular bones. Their bones are more vascular to permit this higher rate of blood flow. Okay. In general, large animals also tend to have more vascular bones. This is kind of just a fact. And another very important fact is that the vascularity of bones, so how much blood flow do your bones permit, you can measure this through fossil records. Okay, so what we're going to do is we're going to try and predict some numeric measure of vascularity of bones using size of the animal. Okay, and we're going to compare dinosaurs to either warm-blooded or cold-blooded relatives. Okay, so this picture I think is more clear than the description, but the idea again is we want to look at vascularity of bones and say, are dinosaurs similar as we scale with size? Are dinosaurs more similar to warm-blooded animals of today or cold-blooded animals today in terms of the vascularity of their bones? Because that might allow us to tell if they were warm-blooded or cold-blooded. So here's an example. Here's the image. This image I will say I ripped from Wikipedia in the Physiology of Dinosaurs Wikipedia page, but also when I post the slides, there's a link here. There's an academic paper which does this originally, minus these cool graphics that somebody added when they put this on Wikipedia to just describe which regression line is which. So what we have here is body mass on the x-axis. So body mass is increasing. And then we have a blood flow index. So this is measuring the blood flow in these animals' bones. So we see that for all animals, as body mass increases, the blood flow index increases. Okay, so reptiles are here in purple, mammals are here in red, and dinosaurs are this top regression line. Okay. And so we see that as we increase for reptiles, as we increase their body mass, their blood flow index increases at a certain rate here. Same with mammals, and same with dinosaurs. Okay, so this image actually contains a 95% confidence interval. So this is a 95% confidence interval for the mean line here, right? And so this is kind of just an interesting application that I found in the wild. So again, the idea is that for a given x, so let's say we have x here, for a given x, this line, or this interval, contains this purple line, the true purple line, because we're estimating this true conditional mean from data with 95% confidence. Okay? And so if we look at this, we can quickly see, okay, dinosaurs appear to be more like warm-blooded in terms of their relationship between body mass and blood flow index than they do cold-blooded animals. Okay? And so people have used this argument to say, oh, dinosaurs must have been cold-blooded. Okay? So just an interesting application. I will say, so let's look at this graphic again, okay? And I'll give you just a moment, but let's look at this graphic again and let's critique the linear model assumptions. So remember, as we've discussed, we cannot the confidence intervals that we've discussed and the prediction intervals, they only hold under this third assumption of Gaussian errors, right? So let's look on the previous slide again, and we'll look from these points to see if we can critique the modeling assumptions to see is this a valid use of these confidence intervals. Okay, so if you'd like to pause for just a moment and think through this yourself, go ahead. So I'm going to continue on and assume that you've thought about this for a little bit. And so let's critique these assumptions. So if we look, so let's start with the first assumption, right? So let's say these purple points for cold-blooded animals. Let's think about the mean zero assumption. Okay, so the mean zero assumption would say that these points, right? They should be their residuals should have mean zero. Okay, and so what we see is, well, if we were to say, are these residuals? So this is a residual, negative, negative, negative residual, positive, and so on. Are these residuals mean zero? And in particular, I see some problems with this region. So in this region, it seems like we have a lack of the mean zero assumption. And what I suspect is going on here is we have some larger and some very small animals and some very large animals, which have some certain vascularity of their bones, right? This looks like an alligator, which in the reptile world is gigantic. And so it looks, I suspect, if I had the data, we could plot this, but I suspect that these points on the outside here are high leverage points, okay, especially this alligator. And so being high leverage means that it exerts more influence on the model, and if you change this point, it will change your estimates more, right? And so relative to these points, which are near the sample mean of the sample mean of these purple points, these points seem to be pulling the regression line up, and we're missing the mean zero assumption here. Okay, for constant variance and Gaussian errors, well, those aren't important if we don't satisfy the mean zero assumption. And again, I see lack of mean zero. And in particular, what I would like to see here is, instead of a linear regression, I believe that just eyeballing these points looks to me like some slope, like a polynomial regression model would look a little better, right? Maybe even exponential growth here. And so, yeah, so I see some evidence of some lack of some of the assumptions here with these purple points. If I look at these red points, again, I have a very large animal, the elephant over here, which has a lot of vascularity. So the question is, would these be better fit if I permitted a polynomial if I had some polynomial curvature in here? I think this one is less obvious than this example down here of the reptiles, but I might say yes, especially because we have the smallest animal, again, with high amount of vascularity for its size, and the largest animal doing the same thing. Okay, the dinosaurs, what is there, only maybe 10 points in there in yellow, so it's hard to see. Hard to make any generalizable trends with only 10 points, but even so, I think for the confidence intervals for these first two, it looks like maybe mean zero is not satisfied, and then I'd want some curvature. So in general, that's just how you would break down this this example here. Okay, so let's conclude this section. So we can find confidence intervals for everything, right? So that's what we've discussed in this lecture. And confidence, I should say confidence/prediction intervals as appropriate, depending on if we're finding an interval for a fixed parameter, in which case it's a confidence interval, or a random quantity, in which case it's a prediction interval. So we have confidence intervals for the coefficients, beta I. We have confidence intervals for the conditional means of y given x. And we have prediction intervals for y given x. And remember what is the difference between these two, okay? So I've said it many times, but this distinction is extremely important. In general, I do recommend that you use confidence and prediction intervals where the modeling assumptions are satisfied, because this aids in the interpretation of your model. So having a prediction, but not only having a prediction, but a measure of uncertainty around that prediction is important, and tells you, in general, it aids the interpretation, because you can say not only what your prediction is, but how confident you are in that prediction. Okay, and so that concludes the section on confidence and prediction intervals. And next time we will talk about alternative measures of model fit, and I will see you then.